Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another installment of Math 391, Ordinary Differential Equations at the City College of New York. Let's actually just do a recap. I left you guys off with some examples to try last time, which it's very important that you understand those examples for your test tomorrow, which is going to be open as of noon, and the window is going to close at 3. However, whatever time you log in between that, you will have a maximum of 90 minutes to complete the exam, and then you will have until 3 o'clock to upload scans of selected problems. Like I said, I'll send more details of that before the test, but essentially what I mentioned before is how it's going to go down. Now, the last topic that you are responsible for on the test was what we covered yesterday, but of course we have some examples that are going to spill over into today. Hopefully you try them on your own and you're not just waiting on me to do the problems for you, because then you're just putting yourself at a disadvantage. So small recap. A couple classes ago, we looked at solutions to non-homogeneous second order linear differential equations as well as higher order linear differential equations. The highlights from this section are to solve a non-homogeneous nth order linear equation. The general solution is known to be of this form: y equals y sub h plus y sub p. YH is, of course, the homogeneous solution. This solves the equation when there's a 0 on the right side. We looked at how to do that 3 or 4 classes ago. That was over here where we had that table with all the 3 cases. And the form of that is known to be in this form. C1y1 plus C2y2 dot 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 all the way up to Cn where the y1 through yn are n linearly independent solutions. There are solutions that solve the equation when this is 0 on the right side, and the Wronskian of all those guys is non-zero on any interval where you are working. There was also a second component to the general solution. This was called the particular solution, yp, y sub p, right? Now, this is just one specific function that solves this equation with g on the right side. It doesn't matter which one that we do, just in the same way that you can find the equation of a line using any point on the line and a slope. The specific point you use doesn't matter, but from that point, you can actually extrapolate. You can add on to that a slope. That's kind of what the solution here is reminding us of. So it's like finding a fixed point just to do a reference and then spreading out from that using a slope, how you would have done in Calc 3 or Calc 1. You are doing this essentially the same thing with differential equations, because, you know, in the background, differential equations can operate like linear vector spaces. We'll talk about that later on. Don't worry about that right now. But that's kind of why the solution has to look this way. Now, what we looked at last time was ways of finding the yp. We already know how to find the yh, at least in the second order case. We'll talk more about how to find it in the nth order case for n higher than 2. But we saw 2 main methods for solving for the yp. One of those methods was variation of parameters. And it is known for variation of parameters that this works in general. So this is a general method for finding yp. In theory, it can work for any nth order linear differential equation, provided, of course, that you can perform the integration. And of course, if you can't perform the integration, there are techniques by which you can approximate integrals. So in theory, we'll always kind of get something like this to work out well enough for any application that we need it. In the second order case, this formula ends up looking like this, and that ends up helping us find our yp. So in the second order case, y1 and y2 were the 2 homogeneous solutions. We find those using previous methods. Plugging into this formula helps us to find the yp, and we did some examples of that. The second method is undetermined coefficients. That's what we covered most of the time yesterday. and what we're going to continue doing some examples with now. This is equivalent to a method that's very popular, very common, called the annihilator method. So I'm not going to teach you the annihilator method. I'm going to teach you the undetermined coefficients method. In fact, I already did teach you. Notice that this one does not work in general, though. It only works in specific instances. It only works in instances where the right side, your g, is a polynomial, or it's a polynomial times a sine function, or it's a polynomial times a cosine function, or it's a polynomial times an exponential function, or it's a product of all of those, a polynomial times an exponential times a sine, or a polynomial times an exponential times a cosine, or it's just a sum of expressions like that. In that particular situation, we can apply undetermined coefficients. You cannot apply it in general. So if your right side looks like a secant, you can't do it. You can't do undetermined coefficients. Or if it's a tangent, you cannot do undetermined coefficients. Or if it's the right side is 1 over the radical of t squared plus 1, you cannot do undetermined coefficients. You can only do undetermined coefficients in this situation. So that's very important for you to know. Now, we do undetermined coefficients by guessing what our particular solution would be like. The goal is to choose a solution, a particular form of a solution that looks like the G, but not like the homogeneous solution. Right, sine squared would not be covered. So if the right side was sine squared, that is not covered by undetermined coefficients. Right, so because I would have put that here, I would have put sine times cosine, but it does not work. The idea is it only works when your derivatives are self-similar. It turns out if you have a sufficiently complicated combinations of sines and cosines, then their derivatives don't exactly behave predictably. However, if you have a sine and a cosine by themselves, the derivatives are very predictable. You know exactly what they're going to look like. Now, we can choose general forms that look like the YP. Basically, for whatever specific instance of G that is there, you generalize that form to find the YP, and then you multiply, if necessary. You don't always have to do this, but if necessary, if any term of that generalized form looks like a homogeneous solution, you multiply by factors of t, and you keep multiplying by t until there are no more overlaps. So that was the basic idea. And we started doing, and this is the method of undetermined coefficients here, and it just continues with, if necessary, you should be able to find the arbitrary constants. You should also be able to finally say the general solution. We didn't practice any of those yesterday, but we will see examples of that today. We had many examples to get through. We got through a bunch, but we still had a bunch more to get through. So I asked you guys to try this for next time, and hopefully you did. So we are going to start there. So what I can do is get rid of that. Let's move some of these guys out of the way here. Boom. Let's move this to the side. And boom. So now we are ready to rock and roll. And we are we started here on 6/25. 2020. All right, so let's actually jump into this. All right, what is the first thing we do? Let's see who remembers. Go. Find YH. How do I find YH? I don't know what you mean by replacing R. Characteristic equation. What is the characteristic equation for this guy? Right, it's r squared minus r minus 6 equals 0. That is your characteristic equation. You're going to solve this. This looks like it factors. Maybe do a 3 and a 2. Get a minus 3 and a positive 2 should work. This means your r is equal to 3, or your r is equal to minus 2. And so your homogeneous solution is C1e to the 3t plus C2e to the minus 2t. And seems that's what Intra got, so that's good. And arbitrarily, I'm going to choose the e to the 3t to be my y1 and my e to the minus 2t to be my y2. I don't know if that's how you guys chose it, but what is the next thing that we have to do now? Find yp. Now, set yp equals, in this case, our g is 2 sine 3x. So our variable is actually x. And so if it's 2 sine 3x, what is the form of the solution? Form of the yp? Right, a cosine 3x plus b sine 3x. And then you know that this is what you're going to take because there are no overlaps. This here is good since no overlaps with that guy. So that's it. That's your yp here. Okay. Now in this set of examples, we were just finding the generalized form for the yp. I believe were the instructions. Right. Guess the yp based on undetermined coefficients. Do not solve for the arbitrary constants. So for now, we're good. I will do examples with you guys of finding the arbitrary constants just so you know how to do it. But for now, I just want you to get practice on actually figuring out what the yp would actually look like. Here's the second one. And this is going to be very similar. We would find the homogeneous solution first, which gives us we have to start out with the characteristic equation, which is going to be that guy. We are going to see if that factors, which I believe it does. 2 and 1. Minus 2 plus 1. That seems to work. And so we have r equals 2 or r equals minus 1. And so my y sub h is c1 e to the 2x plus c2 e to the minus x. This means that our yp equals, so what is yp here? Right, ax plus b. And of course, there are no overlaps. This is a polynomial. My homogeneous functions are exponentials. So no overlap. These guys are linearly independent. Here is another. So we start out the same. R squared plus 2r plus 3 equals 0. That's characteristic equation. Does that factor? You would guess like 3 and 1 would be the only guys. However, with all these signs positive, not going to work out. So doesn't factor. So what do we do when it doesn't factor? Panic. No, we don't panic. What do we do when it doesn't factor? Quadratic formula, exactly. So r is going to be minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. And so this will be minus 2 plus or minus. This here, I have 1 times 4 minus 3 times 4. So it's 1 apples minus 3 apples. So I have minus 2 apples. So this just becomes minus 2 plus or minus 2 radical of minus 2. And so we end up with minus 1 plus or minus radical 2i. Now, if that is our R value, what does our homogeneous solution look like? Homogeneous solution? And our variable here is x. C1e goes, you're missing something there. You're missing a couple things. So it's C1e to the minus x, right? So minus 1 is the coefficient of the x in the exponential. Cosine radical 2x plus C2e to the minus x sine radical 2x. That's what your homogeneous should look like, which means our particular solution looks like, so our g is e to the x sine x. So what is our particular solution here? G is e to the x sine x. What is the particular solution, or the assumed form of the particular solution? Correct. So it's a e to the x cosine x plus b e to the x sine x. And that's going to be good because no overlap. So there's no overlap with YH there. There was no overlap with YH here. So we're good. Nothing to actually tweak in those examples. Why is Jhevon being so nice? All right, here we have r squared plus r plus 1 equals 0. That does not factor, so we're going to use a quadratic formula. Minus b plus or minus the square root of b squared minus 4ac over 2a. This is minus 1/2 plus or minus radical 3 over 2i. Oh, back to the previous example. Where? Just the answer? Yeah, I saw it like you lost connection and you got back in just now. I don't know where you missed though. So is that good? Okay, all right. So we moved on to this one. we have that, which, well, yeah, that's correct. But I was going to ask that in a bit to see who I could catch with it. Nice. Thanks for stealing my fun, Jason. And I mean, Zkong actually did it a little bit earlier as well. So here you would say YH is equal to, here you'd say YH is actually equal to C1e to the minus x over 2 cosine radical 3 over 2x, or now I'm used to writing x's instead of t's. The variable here is t. Minus t over 2 cosine t plus c2 e to the minus t over 2 sine radical 3 over 2t. And at this point, I was going to be like, so guys, what is the yp? And then I expected someone to tell me something like, well, is it a cosine squared plus blah, blah, blah? And then I'd be like, no! But you guys already kind of messed up. Just so you know, cannot use undetermined coefficients here. So somewhat of a trick question. So for this particular example, if you wanted a particular solution, variation of parameters is how you'd go about it. Undetermined coefficients isn't going to work. Because realize here, you start, take a derivative of sine squared, you're going to get 2 sine x cosine x. Take a derivative of that, it's going to be a product rule, it's going to split into 2 terms. Take a derivative of that, now each term of that is going to split into 2 more terms by the product rule. Things just start getting huge, they start getting messy, they stop getting predictable. So undetermined coefficients would not be what we use here. So that was just a question I threw in to see who was paying attention. All right, now challenge problem. Did anyone figure this out? I mean, technically, this is chapter 4 stuff, but I think you guys really know all the information. If you kind of just follow your nose and naturally kind of guess your way, what you would do, you can kind of find your way here. So I thought it would be fun to just throw the question out there. Does anyone see? And it's also going to test your knowledge of being able to come up with a good YP and YH. Did anyone actually try this? If so, what did you do first? Right, so you started out with the characteristic equation. So it's r to the 4th plus 8r cubed. And this is kind of a foreshadowing of things to come. Essentially, when we have higher order linear differential equations, the process is exactly the same, except you just have larger polynomials to solve. Now, that in and of itself can be something that's difficult in general. And so most of chapter 4 is just going to be me reminding you about how to factor higher degree polynomials whenever possible. But essentially, that's what we're going to do. This, how would you solve for r here? Right, r to the 3 is a common term. We'd be left with r plus 8. And so I would have r equals 0 or r equals minus 8. Now again, remember, we want 4 solutions because this is a 4th order, which means the multiplicity is given by the power of r that we solve for. So the r equals 0 actually accounts for 3 repeated solutions. where the fourth solution is accounted for by the -8. Now, if knowing that, how would you guess that y, yeah, you have r equals 0 essentially. R equals 0 is a solution with multiplicity 3 is how we call it. So it accounts for 3 solutions. So you kind of think of the solution as 0, 0, 0, and -8. So let's see who's, nope. Right, so one is C1 e to the 0, right? So C1 e to the 0 means e to the 0 is just a constant. So you expect to see like 4 constants here, which is what was suggested, but it's not correct. Plus the 3 constants, plus the fourth guy is going to be 4e to the -8t. However, there's a problem with having 3 constants in a row because they're all linearly dependent. You could absorb those all into one constant. Right, and so Incha has it. To create linearly independent solutions in a repeated root, you just keep multiplying by t. This is the principle that we've had before. So that would be what the solution is. So a constant is a solution in one case, multiply that by t to get a second linearly independent solution that's similar to the first but linearly independent. Multiply by t again, you get a second linearly independent solution that's similar to the first but linearly independent. So that is what your YH should look like. Now, that being said, how would you choose YP? And just to remind you, because it's all the way up here, this is your G right here. All right. So now we have the G and we have the YH. What would YP look like? Any guesses? Okay, so it's a combination, right? So you're going to choose a YP that corresponds to the T squared. You're going to add that to a YP that corresponds to this guy. And you're going to add that to a YP that corresponds to this guy. Okay, yeah. So knowing that, what are you going to write down? What is a YP that corresponds to the first guy? The T squared. Right, so here you have AT squared plus BT plus C. Now, before we move on, we check, are there any issues with this? Yeah, in fact, that's exactly the same as C1 plus C2T plus C3T squared. How do I fix it? Well, this is interesting. We just had people like counting up, multiply by t squared. No, multiply by t cubed. No, multiply by t to the 5th. No. Can I hear a 6? Can I hear a t to the 6? Well, we can know how much we have to multiply it by just, it's not that high. We can actually start counting it. Multiply by t. Would there be any overlaps? Yes, because then this would give me a bt squared and a ct, which is going to overlap with those two. Multiply by a t again. Will there be any overlaps? Yes, because if I expand this, there will be a ct squared, which is going to overlap with the c3t squared. Okay, multiply by a t again, t to the third. Is there an overlap now with the homogeneous? The answer is no, because I would actually have, after that, at to the fifth plus bt to the fourth plus ct cubed. None of these are a squared or a t squared. None of them are a t. None of them are a constant. So that actually is what the correct first part should be. Plus, now we move on to the second one. So technically here your t to the k is t cubed. But then if you multiply it out, you end up with, it's not quite a 5th degree polynomial because notice it only has 3 terms instead of 5, but it is a 2nd degree polynomial that we just multiplied by a cube. So the degree is 5, but it's not the general 5th degree. All right. So now what does the second part look like? Right, so now we can't assume that we can't reuse arbitrary constants, so you just go one more, d e to the minus 2t. Then we go and we check for overlaps with yh, and there are none, so we can move on. We're good here. So that would be the second part, d e to the minus 2t. What about the third part? What's the third part? Right? Arbitrary constant e to the minus 2t cosine rad 3t plus f e to the minus 2t sine rad 3t. And check for overlaps with the homogeneous. You'll quickly notice there are none. And so that leaves us with this part here. It would not matter if there's a negative at the original, because what? You mean this here? No, because this e here is an arbitrary constant. If it turns out that it has to be negative to get it to work, when we solve for e, we'll find a negative answer. So you always do this generic form here. So that is what we'll have. We will have okay. So that was a little challenge there. As you can see, that really tests your ability. Do you understand how to deal with repeated roots? Do you understand how to develop a YP, how to tweak the YP to account for overlaps with the YH, right? There are a lot of different terms to do. And sometimes, in fact, I've seen this in finals, and occasionally I put it on tests myself, where you would just be given an equation like this, and the whole point of that question, because it's super long and ridiculous, no one's going to ask you to solve it fully, but the whole point of the question is to come up with this generic form here. Right? So know how to do that. Like if you know what the homogeneous solutions are, you should be able to come up with a particular solution that will correspond to a given G and at the same time not overlap with any of the homogeneous. You should know how to construct such a problem. Yeah. All right. Now let's do the culminating example. We are going to do a full example from start to finish with all the bells and whistles. Not only are we going to find the general YP, we're going to find the specific YP that is going to get the job done. Then we're going to apply initial conditions to find the arbitrary constants for the homogeneous solution. So this is like a full-fledged, fully worked out problem. So normally on a written test, this would just be like one complete problem where this is it. Problem 3, solve this fully. Boom, and there you go. That's problem 3. Have fun, right? So now let's actually do that. Now the beginning starts out innocently enough, so let me just do that for you guys. Hopefully you guys got the same thing. We run right into our characteristic equation. Does that actually factor? I believe so. So we know that R equals 2, but it's a repeated root. So this would ultimately mean that my YH is equal to C1 e to the 2t plus C2t e to the 2t. All right, that being said, what is my YP here? So where you guys come in, what is YP? No? Any other guesses? Now they're getting exotic. Okay, so here's how we're going to choose our G. So our YP. So I'm going to look at the G, and term by term, I'm going to develop someone that is going to model that term in the YP. So that is a t squared, which is a second degree polynomial. I am going to write down a general second degree polynomial. That is going to correspond with this guy. I'm then going to check my YH for overlaps, and I realize there are none. So I'm simply going to move on. Now I look at this part of G, and I'm going to write down what would work there. So that's just a constant times e to the 2t. So I'm also going to have a constant times e to the 2t. Now I look for overlaps. YH, oh, there's already a constant times e to the 2t. So I multiply by t. Check for overlaps again. Oh, there's also a constant times t times e to the 2t. Multiply by t again. And that is that. Yes, intro was right. What do you mean why there's no overlap? The first part is just t squared. Nothing here overlaps with t squared. I have an exponential and then a polynomial times an exponential. Those guys are very different from just a quadratic. Why is there no overlap for the first part? Okay. Yeah, so remember, YP is chosen based on the G, which is the guy up here. So you start out by making it look like that. So we put a generalized quadratic and a generalized constant times e to the 2t. Then we tweak it so that to prevent overlap from our YH here. So I only start tweaking things if I see terms in my YP that match guys like that. So in the first part, in the green part, there was no need to change anything because there is no constant or a function of t, or there's no constant or a constant times t or a constant times t squared in the YH. So I can leave that alone. Moving on to the second part, if I write a constant times e to the 2t, that is going to overlap with the C1 e to the 2t. So I multiply by t to kill that overlap. But then I realize it now overlaps with the C2 t e to the 2t. So I multiply by a t again to kill that overlap. Ultimately, we now end up with this guy. So that would be our YP. Now, this is not the end of the problem anymore. This is the starting point of the problem. Okay, so now, how do we actually go about finding the A, B, C, and D? That is what's necessary for this problem. Now, the process is going to be very similar to, again, many processes here are going to be likened to processes in Calc 2. I mean, mechanically speaking, this class is very similar to Calc 2. It's going to be very similar to the process of partial fractions. The idea is you're going to plug this into the original equation and solve for the arbitrary constants by equating coefficients. And so here, the only difference is before we can actually plug it in, we're going to have to take derivatives because I'm going to have to know what y double prime and y prime is so that I can plug it in. So I'm going to move on to finding derivatives, yp prime. I would have 2at plus b plus 2dt e to the 2t plus 2dt squared e to the 2t using a product rule on the second part. I would clean this up a little bit because like I was mentioning before earlier, we want to minimize the amount of expansion we have to do. So I realized that if I wanted to differentiate this guy or that guy, I'd have to use the product rule. That means I have to use the product rule twice. That means it's going to expand into 4 terms. I'd like to minimize the expansion. And so I combine those guys into 1 term so that I only have to do the product rule once. And so that leads me to yp double prime. So that now becomes 2a. Derivative of b is just 0 because b is a constant. And then I'm going to differentiate the polynomial part plus, and now I'm going to differentiate the exponential part. And once again, let's just group these guys here. So basically here now I have 4dt plus 2a plus 2d. That's the polynomial part of my yp and the polynomial times exponential part of the yp. Now what we're going to do is plug into the ODE. just to remind you of what that is, that was the guy up here. Yes, this is a part of undetermined coefficients. All right, so now you're going to plug in. All right, but the rest of this is algebra, really. So I'm going to take the y double prime, which is this guy. Then I'm going to subtract 4y prime, which is this guy. And then I'm going to add 4 times y, which is this guy. And then I'm going to set all of that equal to the right side, t squared plus 12e to the 2t. Okay. So this guy here is the yp double prime. This guy here is minus 4yp prime. And this guy here is the plus 4yp. So that's my differential equation. The y double prime minus 4y prime plus 4y. So that's this guy. Plug that into the left side and set it equal to the right side. Now what I'm going to do is I'm going to start group things together. So this comes down to going to the right, I'm going to group, let's say, group all the t squares. So I have t squares time. Now I'm going to go and group all the t squares. Ever I see a t squared by itself, I'm going to grab it. I have one here. That's 4a t squares. Any more t squares? No, that's it. Plus, now I'm going to group all the guys that have t's attached to them. I have one here. That's a bt, 4bt. I have a t here, minus 8a. I have a t here, plus 4 dt. And those are all the t's. Plus constants. go in and find all the constants. So I have one here for C. I have another here, minus 4B. I have here, minus 2A plus 2D, plus 2A plus 2D. And those are all the constant terms. Okay, now plus, where are all my t squares times e to the 2t's at? I have one here. So 4D. I have another 4D. I have another one here. So that's going to be minus 8D. I have another one here. It's plus 4D. Plus, where are all my TE to the 2T's at? I have one here. I have one here. That's minus 8D. And I have one here. That's 4D. That's all of those guys. Plus any guys just attached to e to the 2t. Nope, there's no one just attached to e to the 2t. Although there should be. Did we miss anybody? Oh geez, we did miss somebody. Ah, here. God, that's going to be a nightmare. We're doing so well. Okay, let's see here. Oh, all bets are off. What happened? Did I just copy I copied YP double prime here. Oh, yeah. Oh, that would have been a whole other thing. So YP double prime goes in this position. Where were you earlier? Tell me that I missed this e to the 2t. And the YP prime. Yep, that's how it is with these problems. And the Y. Fix that. Yeah. So this is like to correct this is it's probably gonna take longer than it would take to actually just do it again. Okay, so let's double check. YP is AT squared plus BT plus CT plus DT squared E to blah blah. Looks like fine. YP prime is that guy, which hopefully is fine at this point. Then the YP double prime is the guy that I just copied from here. Group the T squares. 4A. Well, one thing is, at least if you make a mistake here, I mean, a problem wouldn't be this long on an exam, but if you make a mistake, at least you probably should know because you're going to realize something is missing. Because I realized a mistake was made when I got to this position here and I had 0 e to the 2 t's on the left side, but there's supposed to be 12 e to the 2 t's on the right side. So I can't have 0 e to the 2 t's on one side and 12 on the other side. So that kind of indicates to me, oh, I missed something. Something was off somewhere. So yeah, now I think we have that. And I think the t squares, now I have another one, 4D. No, that guy's attached to an exponential. So I still only have 4a t squares, so that doesn't change. How many t's do I have? Well, I have 4b. Minus 8a. 8d. I think those are all the t's. constants for C. What wouldn't go where? The 8D. You mean this one right here? Where did I put that? Did I put that here? Okay, yeah, that shouldn't be there because that's attached to an exponential. Geez, scrolling up and down is really... Scrolling up. Now I'm looking for constants. So there's the 4C. Minus 4B. Plus 2A. Plus, now look for t squares e to the 2t. And I would have 4D. Here, I would have minus, I would have 2D t squared e to the blah, but then I multiply that by 4, so that's minus 8. And then up here, I have plus 4D. So that's all going to cancel out to 0, but I'm actually not worried because there was no t squared e to the 2t over here. So that's not particularly alarming. Moving on to t e to the 2t. I have 1 here. That would be minus 8d. I would have 1 here. That is plus 8d. Again, that simplifies to 0. Not too worried because there was no t e to the 2t there again. Now I just want a constant times e to the 2t. And pretty much everyone's canceled out except this guy, 2d. And all of that is equal to t squared plus 12e to the 2t. Brings us to the next step, equate coefficients of like terms. So basically that just means you're matching guys up. The number of t squares on one side must be the number of t squares on the other side, etc. So you know that 4a must be equal to 1 because there are 4a t squares on the left, and there must be equal to 1 t squared. 4b minus 8a must be 0. So 4b minus 8a must be 0. So this was the t squared coefficients. This here is the t coefficients. Then the constants, there are no constants. So 4c minus 4b plus 2a equals 0. Four c minus 4b. Then the t squared e to the t. Well, these guys cancel each other out, so I don't have to worry about it. These guys also cancel each other out, so I don't have to worry about it. And finally, 2d must be equal to 12. And this comes from the e to the 2t coefficients. So now I have 4 equations, 4 unknowns. So you get a system of equations. So now you just solve the system. So of course here we have a equals a fourth. We also have d equals 6. And so this means that if I have 4b minus 8 times a fourth, I would get 0. So this is 4b minus 2 equals 0. So this means that our b equals a half. And finally, now we can actually find c. So 4c minus 4b plus 2 times a is equal to 0. So we have 4c minus 2 plus a half equals 0. Multiply by 2, I guess. Get minus 3 over 8 for c. Did I make a mistake somewhere? How did you get c equals 6? Yeah, it's someone got 6 though, but I'm not sure. Anyway, ultimately, this means that yp is going to be, you go back to the original yp, which you know is this guy. And they're going to fill in the numbers. A is a quarter. B is a half. C is 3/8. And D is 6. That's our particular solution. This means that the general solution is YH plus YP. Our YH. So no, we're not done. E to the 2t with a repeated root. This means, of course, y prime is going to be 2c1 e to the 2t plus c2 e to the 2t plus 2c2 t e to the 2t plus a half t plus a half plus 12t e to the 2t plus 12t squared e to the 2t. Now, apply our initial conditions. So y of 0 is 1, y prime of 0 is 0. Okay, so I would go to y, I would plug in 0 for t, and I would set that equal to 1. 1 is going to be equal to C1 plus 3 over 8. And 0 would be equal to, if I plug in t equals 0, 2C1 plus C2 plus a half So from this, I get that my C1 is going to be 1 minus 3/8, which is 5/8. And from this, I would get that my C2 is going to be equal to minus a half minus 2 times 5/8, which is 5/4, which is minus 7/4. So this means our y finally is going to be equal to C1, which is 5/8 e to the 2t plus C2 minus 7/4 t e to the 2t plus the particular solution. No, your initial conditions come last. In other words, you can't find the C1 and C2 by using the YH alone. Well, it would depend if you were working on a homogeneous versus a non-homogeneous answer. Otherwise, it may have been a coincidence. But in general, your coefficients need to fit the general solution. Right? Because you're told, notice that you're told y of 0 is 1 and y prime of 0 is blah, right? Y of 0 is not the same as YH. Y is YH plus YP. So you have to plug in, you have to find the C1 afterwards. And boy, I hope the arithmetic is right there. I'm not even gonna check it actually. So that was a pretty long problem. Normally, if you're seeing something like this on a test, you wouldn't have a sum right here. So your YP is going to be smaller by default. And you plug it in, it's going to be a little bit nicer. But I decided to give you a problem that kind of has all the bells and whistles, like the worst case scenario that you would see, maybe even in the homework. There are not going to be many problems that get much crazier than this one. So you just have to be very careful with your arithmetic and your algebra and don't miss anything. Hopefully if you're writing on a page and not scrolling back and forth, it's not going to be so bad, but yeah. There we go. So that's like a full problem. That actually combines a lot of things that we've studied. This involves knowing about homogeneous solutions for a second order, knowing about what it means to find initial conditions, knowing about how to choose a particular solution, and how to actually find constants C1 and C2 that will match initial conditions given. This is a full problem called an initial value problem. It's a non-homogeneous initial value problem. And this is what a complete solution to that would look like. So if we had a situation that's modeled by this differential equation, and I know what the initial position is and what the initial velocity is, I can predict what the quantity y is going to do at any time in the future for as long as this model is applicable. Now, besides the fact that we can check the arithmetic here and whatever, do we have any questions about the process? Because we actually put together a lot of processes here. So we have this non-homogeneous situation. First thing you want to do is find the homogeneous solution. Start with a characteristic equation. Based on its solution, you come with a homogeneous solution. Then you choose the YP afterwards, because your YP needs to look like the right side, but at the same time not overlap with any of the homogeneous solutions. So that gives you that we ended up having to multiply by an Exert t squared here. Then you find all the derivatives of that particular and plug it into the original. This will allow you to group like terms and set them equal to the right side, which allows you to get a system of equations. And solving for those guys will give you the actual particular solution that you were looking for. And of course, there are times when you don't have a system of equations. The problem can be small enough where there's literally only one equation. There was one arbitrary constant a, and you can get an equation that says a equals this. Once you're done, you find y. Y is the homogeneous plus the particular solution. Then you want to make sure that you plug in those initial conditions into y if required, and that allows you to find the C1 and C2. Ultimately, your answer should look like this for this problem, or something like this. I'm not promising that this arithmetic is correct. And at this point, I'm just too tired to check it over. Variation of parameters works in all instances. Variation of parameters is a general method. The one that you have to worry about that might not work is undetermined coefficients, actually. Now, I didn't actually do variation of parameters for this. You guys can try it and see if it would be a way that you would prefer. However, to be fair, coming up with this expression here, at minimum, you should know how to do that. Even if variation of parameters is something that you prefer doing, you should at least know how to construct the YP. And because that is often asked. That is something that you can reasonably expect is pretty likely to come up on like a departmental final or something, where they'll just give you like this huge equation and they'll just say, find the form of YP, you don't need to solve for the arbitrary constants, right? There are questions like that all the time. So you need to know how to do at least this. And of course, in theory, you need to know how you would actually go about finding the arbitrary constants once you've done that. However, in practice, if you stick to variation of parameters all the time, it'll always work. So, yeah. All right. But to reiterate again, variation of parameters is the general method. It works in all instances. The undetermined coefficients, the process that we're doing here, does not always work. It happens to work in this case because we have a polynomial and a polynomial times an exponential, which is one of the nice forms. All right. Now, I think for the remainder, I just want to set up the next section. You're not responsible for it on the test, but as a bonus, I might actually just set one of these problems up. It turns out that the next thing we want to cover is a specific application of second order linear differential equations, believe it or not. There are many applications that are done in section 3.7 and 3.8. We are going to pick one of these applications. Namely, it's called spring mass problem, which is essentially us trying to measure the motion of a mass that's at the end of a spring, and the spring is vibrating. So essentially, this is the setup. You have some spring, it's hanging from something, and its natural length is L, right? So no spring minding its business, its length is L. Then we attach a mass to that spring, right? It extends it extra by a length big L, right? And then everything is fine, all is right with the world, but for science, of course, we mess with it. We go boop, we boops the system, like you hit the mass or something and the spring starts bouncing up and down, right? Now the distance in which it's bouncing up or down, we start to measure that by a function U. So that's a spring mass system. You have a spring, someone attaches a mass to it, and then boop, someone either hits it or they stretch it further down and they release it. And so this thing starts oscillating up and down. It just keeps, bouncing, boom, 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 boom. It starts oscillating like that. Now, at the end of the day, our goal is to figure out what is the position of this mass at any time t. In other words, we want to measure the function u. Can I predict what u will do at some point in the future? That is the goal. Now for that, we need some preliminaries. I'm gonna have to remind you of some physics concepts that I'm sure all of you know, but let's just go over them. One thing that is strange that I do need to point out, so this is preliminary 0, but it flies in the face of how we normally do things. So I just want to point it out. For this application, we consider the downward direction to be the positive direction, which I know is weird. In most of your physics application, you are taught that up is the positive direction and down is negative. We're flipping that on its head here because the spring is hanging from the ground. So in some perspective, the top of the spring is down here towards the bottom. And that's where the mass is going to be attached. So we just think of the downward direction as the positive direction. Of course, calculus of motion is something I want you to remember. If I say u is the position function of the mass, then that means if I take u prime, that's the velocity. If I take u double prime, that's the acceleration. Newton's second law, very important law by Newton. Force equals mass times acceleration, right? So if you have a mass m and acceleration is a, the force required to accelerate that mass by that acceleration a is given by this equation. Specifically here, if our acceleration is u double prime, then the force acting on the system can be interpreted as equal to m times u double prime. Newton's third law, for every action there's an equal and opposite reaction. We're going to be using that to balance our free body diagrams to kind of figure out how these forces are going to interact with each other. So we'll be using that from now and then. Does anyone remember Newton's first law? What's Newton's first law about? So here we're using the second and third. Anyone remember the first law? Right, that's the one about inertia. An object at rest will remain at rest, and an object in motion will continue in motion in a straight line unless acted upon by an external force. That's Newton's first law, the law of inertia, right? Another important law is Hooke's law. So this is a law that governs springs and how they work. It turns out that the force needed to stretch a spring by a certain length is actually proportional to the length that you're stretching the spring. This was discovered by Hooke's law. That's mentioned here. Now, the constant of proportionality, this depends on the physical properties of the spring, how big it is, how thick it is, how tightly it's coiled together, all that good stuff. But for each individual spring, you can actually figure out what this constant of proportionality is. We call this constant the spring constant. essentially what Hooke's law says is F is equal to Kx, where F is the force needed to stretch a spring by X units beyond its natural length, and K is the spring constant. Use our notation here, big L was the extra that the mass stretched the spring. Fs is what I'm using for the force to stretch that spring, and I put minus here because, again, we're thinking of the negative direction as being up. So if the weight of the mass is pulling down, the spring constant is going to resist that force because of Newton's third law. It's because every action has an equal and opposite reaction. So the mass is pulling the spring down. So the spring constant force is the spring is going to exert a force up, which is the negative direction. And so that's why it's negative Kx here. Then I look at what L is. Now L, big L, was what the mass stretched the spring before it was in motion. But now we're actually stretching it by a little extra. So we are going to be extending the spring equivalently by big L plus U, right? Where U is equal to 0 means you're in the starting position, which we call the equilibrium position. So I can rewrite Hooke's law using our notation in this particular form. I do also expect you to remember the acceleration due to gravity. That is 9.81 meters per second squared, or 32 feet per second squared if you're empirical units. Gravity, the acceleration due to gravity is experienced differently depending on where you are in the globe, but that's the standard accepted average. Of course, by Newton's second law, weight equals mass times gravity, because weight is a measure of force. Mass and gravity is the acceleration due to gravity. So F equals ma is equivalent to saying weight equals mass times gravity. So that I expect you to remember. And by the way, I'm naming these equations. That one happens to be equation 4. There's also something called a damping force. Now, damping force for us is resistance force. A lot of times these guys are ignored in physics, right? So these would be guys like air resistance or the resistance of fluid to motion. And there's neglect air resistance. So whenever they say that, they're really telling you neglect the damping force, right? So there's something called a damping force. And you can also pretty much empirically verify that damping forces are proportional to the velocity, right? This is why when you're running, you feel more wind in your face than when you're walking. You experience more air resistance when you're running faster than when you're moving slower. It's because the resistance you'll experience in a medium will become greater the faster you're moving through that medium, greater in a proportional sense. Basically, this is saying if Fd is the damping force, it is going to be proportional to the velocity of our system, which is u prime. And again, negative here, because the damping force is going to be pulling upwards, because the spring is going downwards by gravity. The air resistance is going to blow towards the bottom of the mass and try to pull it upwards. And so that's why that's negative there. So that's that equation, equation 5. All right, so those are our preliminaries. Let's actually move on to how we're going to figure out this application. So this ball right here just represents the mass at the end of the spring. The weight that is pulling down is the force that's pulling down. That is W equals mg. And again, the spring is going to have an equal and opposite reaction of Fs. That is measured by Hooke's law. Now, because initially, if we assume that the body is not moving, we call this position equilibrium. And this basically means the upward force and the downward force are equal in magnitude. Or, as some of you might have heard the phrase in physics, the sum of the forces acting on the object is 0. That gives us the following. mg minus kl must be equal to 0. If I take the mg plus the minus kl, they all sum to 0. This means the object is in equilibrium. So the system currently is not moving. That's how it's going to start out. Now, we're going to measure the force in 2 different ways. We're almost at the end, bear with me. It's going to be really cool when you see how this all fits together, and it's going to pop into something familiar, just like almost out of nowhere. One is to measure the force experienced by this spring system using Newton's first law. So force equals mass times acceleration, Newton's second law. Force equals mass times acceleration, so that's mu double prime. Another way to measure it, though, is to actually think of the free body diagram and measure all the possible forces one by one that our model is taking into account. Another way to actually do that is to say, well, what are the forces acting? Well, there's the weight that's pulling down. There's the spring that's resisting this pulling down by pulling up. There's also the air resistance that's resisting this. And there's a big F of t. Now, big F of t represents human intervention, let's say. It represents some external force that may or may not be acting on the object. Of course, if there is no mention of any external force, we assume F of t is 0. But as a placeholder, let's be safe and leave it in there. So those are all the possible forces that our model is taking into account. Now, this force must be the force by Newton's second law. This force must be the force by our free body diagram conception, which means these two forces must be equal. So we set them equal and we obtain this. Now I'm going to use some of my previous equations. I saw that my Fs is this expression here. I saw that my Fd is this expression here. So I'm just going to go and plug those guys in right here. Expanding the parentheses, I get this guy. You'll notice that guy includes an mg minus kl. We found that in an equation that mg minus kl is 0. That comes from equation 6. So I plug that in 0. Now I clean things up, move to the other side, and boom, there it is, guys. That equation models the motion of the mass at the end of the spring. Now, the perspicacious about, I'm just too tired, can't even say perspicacity right. The insightful, let's say among you, will notice, hey, that's a second order linear differential equation. Right, and it's a non-homogeneous one. It's non-homogeneous as long as the external force, is actually measurable. It's non-zero. However, if there is no external force, it's a homogeneous, right? So that leads to this application. And we can summarize by the following. The motion of the mass at the end of a vibrating spring, if u of t is the function that is measuring its position, then this differential equation will model that motion. In this equation, m is the mass, gamma is the damping coefficient. This is the constant of proportionality for the resistance force. K is the spring constant, and big F of t is any external force. Your u of 0 is the initial position. Your u prime of 0 is the initial velocity. Some things to keep in mind. Again, I probably should have repeated here that upwards is our negative direction, downwards is the positive direction. But of course, if we know that the system begins in equilibrium, we assume that the initial position is 0. If we say the system is just released, like someone stretches it and then just lets go, this is initial volume is 0, initial velocity is 0, and otherwise we will tell you what the initial velocity is. Mass is computed by weight divided by gravity. The spring constant is computed by weight divided by the length stretched by the mass. Gamma is resistance force over velocity. So a problem might tell you something like, oh, a force of 2 pounds is experienced. A force of 2 pounds of resistance is experienced when the mass is traveling at 1 foot per second. Then 2 divided by 1 would be your damping coefficient. Make sure all your units are consistent, right? So don't measure units of length to be feet over here, and in another part of your problem, it's meters. Make sure all of these guys are consistent. This one is just basically to say there are many other applications covered in this section and many other angles of this application that is covered in this section, but we are going to ignore them. The interested reader can read further. So this section also covers applications of second order linear ODEs to electric circuits. It talks about things like quasi-period and over damped motion and critically damped motion, etc. We're not going to mention any of that. You don't need to know. Pretty much what you need to know is if anyone describes a scenario like this, you need to be able to develop a second order linear differential equation to describe it. And then you need to be able to solve that second order linear differential equation and then answer any questions, simple questions that might arise from that. Here are some examples. So if you guys have time, you can practice doing the setups here. But otherwise, it's not going to be terribly important for the test, unless it's a bonus. Maybe I'll just quickly take a minute and set up one of these guys, so that if you want to attack the bonus problem, you'll have some experience with it. So, for example, let's do this one. Now, I want to fully solve this, but the fully solved part you guys can take care of because you now know how to fully solve a second order linear differential equation. So let's actually just do a setup here to see what this guy will actually look like. Okay, so we can read it. A force of a 2-pound weight stretches a spring 6 inches to a position y equals 0. Set up an initial value problem for the position y of t if the spring has been stretched down another 6 inches and is released. Now, as I mentioned here, we are going to fully solve this problem, but for now, I will just give you guys I don't know why I did that. Did I do Control Shift? I'll just give you guys the setup and we'll read through the setup. Okay, I don't know what I did. Let's just move on. So once you know how to read these, the setup shouldn't take you too long and probably shouldn't be too complicated. You start by reading it very carefully. So we know that the weight is 2 pounds. And that is the force that stretches a spring 6 inches. So we know that our L is 1/2 a foot. Now I'm using feet because, of course, if I want to use gravity or anything like that, I'm going to use feet, not inches. So that's how much it stretches the spring. Now, this tells me a bunch of things. First of all, I can now figure out the mass. Because weight equals mass times gravity, the mass is going to be W over G. This was mentioned in the bullet points earlier. So this is going to be 2 divided by G, which is positive 32, or the mass here is 1/16. Also, Hooke's law, remember F equals Kx, so the weight is going to be the weight divided by this length stretched is going to be the spring constant. This means this is 2 divided by 1/2, which is 4. Now, gamma is 0, not mentioned, right? So no resistance was mentioned, so I'm not gonna even bother plugging that in. And that leads us to our setup. It turns out that 1/16 y double prime plus 0 y prime plus 4y equals 0, because no external force was mentioned, will model this, this system. On top of that, I know that y of 0 equals 0. No, I think they told us they did something. It says it has been stretched down an additional 6 inches, which means the initial position is 1/2 a foot lower than equilibrium, and the initial velocity is 0 since it was released. How do we know L? It's mentioned here. It says a weight stretches the spring by 6 inches. L is the length that the mass will stretch the spring. Big L, that's what it is. So 6 inches is 1/2 a foot, and so that's Ellie's 1/2. And so that's it, that's the setup. If you solve this second order differential equation, no, little L is the natural length of the spring. Without anything attached to it, little L is the natural length of the spring. Big L is the extra, right? So little L is what is how long the spring was before any of this started, when the spring was minding its own business. And then big L is what we get, is the little extra that the spring is stretched when the mass is attached to it. Then when it's set in motion, the spring is extended even more by a function u, where u is measuring the distance of the mass, displacement of the mass from the equilibrium position. So you can read these, pick these guys out. Another thing you might have to pick out is the gamma. Another thing that could be inputted here is an external force, but if there is an external force, it's going to specifically be mentioned. So you don't have to figure out external force. You might have to figure out gamma, but in this case, there was no resistance mentioned. But in general, if a resistance is mentioned, you can figure it out from this. So they'll tell you what the resistance force is experienced at a certain velocity. Some problems would even just tell you straight up, gamma is this, the damping constant is that. Here, in this question, they told you that, yes, little l is irrelevant for the setup. Yeah, big L is what's important. Little l is placed here just for emphasis. Hooke's law, the length that Hooke's law talks about is the extra length. So we kind of always want to make a distinction between the extra length and what the length of the spring was before. Because the length component in Hooke's law is the extra length. It does not include the natural length. And that's why we tend to measure it separately. So little l is not important for our setups, but theoretically it's important for the setup, because the L for the length that we need for the setup is the length not including the natural length. Right. So that is a pretty cool application of second order linear differential equations. Again, you're not responsible for this on the test, technically speaking. However, in the bonus, I'll put a problem like this and ask you guys to just do a setup maybe. There would be no point in asking you to solve that, because within the test itself, I'll actually ask you how to solve it. Or maybe I'll tell you what the solution is and then ask you some questions about it. But yeah, I'll leave these guys here. We'll fully solve this next time. But that's really using information that we already learned. And that's it. That's all I have for you guys today. We are going to wrap up there. Yes, I did open all the sample tests, so you should be able to get in. That was open as of yesterday evening. The test will open at noon. You have to complete the test by 3 p.m. This includes, after submitting the test, scanning your work and uploading it. The test itself will last 90 minutes, an hour and a half. So you will effectively have a whole other 1 hour and a half to scan your work and send it in, which is way more than enough time. That's like, to scan your work should be like a 10 or 15-minute process if you got the apps on your phone that I asked you to get. So we'll end there. Good luck tomorrow, guys. Hopefully you continue with the practice. What I would say for now is really, if you haven't finished all the homeworks for the sections, I would not spend the time doing that right now. So yes, it is multiple choice. But there, of course, any problem that asks you to do calculations, I expect you to write down your calculations and scan that. I'll send you instructions on where I want you to do this, but I don't want you to email it. It will be uploaded in Gradescope itself. So you'll see Gradescope at noon, you'll see the test appear, and then you'll see another thing appear that says test upload. So you're gonna go into the test, you're gonna take the test, but make sure to write down your work neatly on a piece of paper. And then once you submit the test, then you take pictures, scan your work, and then you upload it to the other assignment. Yes, I'll email you a reminder with specific instructions. And the window is 12 to 3. Which means technically you can start it at 1 o'clock and you should still have enough time. But you would be able to access it as early as 12. Yeah, you can. So the deadline for the scan is 3. So you can scan it at any time. You can send in your scans at any time, from 0 minutes to the 3 hours. But first, go to the test. Go to the test. Do the test. It's going to be about 20 problems, but some of those, they are going to be like definitions based. So there are going to be some problems where you don't have to do any calculations. It's just going to be me testing you. Do you know this definition? Do you understand this concept? Pick the thing that sounds right. Right? No calculations necessary. So you'll have a few questions like that. Then there'll be some questions where I'll ask you to set stuff up. Like word problems where you have to set stuff up. And then you'll have some questions where you have to fully solve it. I'll also have things like identification problems as well. Identify if whether you have a linear equation here, or is this an exact equation, or is this a blah, or is this a blah, right? So a lot of problems will be similar to problems that you did on the quiz. For the longer type problems, the sample test on the website will give you practice on those. Just at the very least, make sure you know how to set up one of these word problems. So that will be the tank problems, you should know how to set them up. Population problems, you should know how to set them up. Money problems, you should know how to set them up. As a bonus, know how to set up the spring mass problems that I just spoke about. But if you don't know how to do that, it's technically you're not at a disadvantage. Yeah, if it's multiple choice, it will be auto graded. I'd use the scans to actually further assess if something is off. So the scans will just allow me to deal with any issues that might have arisen for whatever technical reason. Yeah, it's like all multiple choice or select all that apply, stuff like that. So doing the actual test, you're just like clicking answers, but you're going to need to prove that you knew how to get those answers by using your scans. Yep. So if you want a pretty good idea of how the questions are going to look, go over the 2 quizzes as well as the sample test that I have on the class website. I'll ask you problems of that type. And just problems that will gauge your general understanding. So I might say, oh, here's a linear equation. What would the integrating factor look like? Or, hey, is this an exact equation? Or things like that. So quite a few of them would be, yeah, like I said, the homeworks, I wouldn't focus on that right now. The homeworks would go a lot deeper than I'm going to be testing you on. Right. Plus the homework, you can use calculators on it and stuff like that. Like for our tests, you shouldn't need a calculator. Some of them, yeah. You should be able to see the answers to the quizzes, actually. If you go in Gradescope, you should be able to see the answers. If not, you can let me know, but I'm pretty sure they should be visible. There should be a place to review somewhere, and you'll see the correct answers there. Anyway, that's it, guys. We're running out over time, so let's wrap up. Good luck tomorrow. You guys know everything you need to know for the test, really. Just do more practice. Look over the quizzes, look over your concepts, all those things that I put in a box in my notes. Make sure you know those things. And you can practice from the sample test on the class website. That being said, let's get out of here. I'll see you guys in the next one. Ciao.